All right, let's jump right in. Have you ever wondered how an app, a website, or even a game just seems to make decisions? How it knows exactly what to do next? Well, we're going to pull back the curtain on the secret of how software seems to think. It's a concept called conditional branching. And trust me, it is everywhere.
I mean, really? Have you ever stopped to think about it? How does an app figure out what to pop up on your screen? Or in a game, how does it know the exact moment your health hits zero and it's time to flash game over? The answer isn't magic, not at all. It's actually a really simple, super elegant piece of logic. And you know what's so cool about this? You already get the basic idea, because you literally use it every single day. When you think, if it starts raining, I'll grab an umbrella. That's conditional logic. Computers do the exact same thing. They just translate that simple thought into code. Okay, so let's start at the very beginning, the absolute foundation of all this stuff, the fundamental building block of all computer logic, the simple if decision.
So, what is conditional branching, really? Well, at its core, it's just a program's ability to choose a path. It asks a super simple question that can only have a yes or no, a true or false answer. Is the user logged in? True or false? Was the payment successful? True or false? And based on that simple answer, it knows exactly which way to go. Let's look at this in action, okay? Here's a tiny bit of code. All it's doing is asking one question. Is the value in age greater than or equal to 18? Well, since age is 20, the answer is true. So the instruction to print "you are an adult" runs. But what if the age was, say, 16? Well, then the condition is false. And the program, it just sees that and, poof, skips right over that instruction. That's the simple if in a nutshell. It only acts if the condition is met. That's awesome, but it brings up a good question, right? What happens when the answer to our if question is no? We need to give the computer a plan B. And that's where the if-else structure comes in, and it's just so simple and powerful. It tells the computer, if this condition is true, do this one thing. Else, which basically means in every other possible case, do this other thing instead. What's great is that this guarantees one of the two paths will always be taken. Okay, check this out. A perfect real-world example from a paywall you've probably seen a million times. The code is checking a single variable, is paid, which right now is set to false. So when the if condition looks at it, it fails. The program then jumps straight to the else block and tells the user payment required. And if we just flipped that one little variable from false to true, boom, the if block runs instead, and you get access granted. It's a digital gatekeeper, and this is the simple logic running the whole show.
But let's be real, life usually has more than just two options, right? So what if we need to check a whole series of conditions? Think about something like a school grading system. We don't just check for pass or fail. We have to check for excellent, then good, then average, and only then fail.
So to handle this, we use something called elif, which is really just short for else if. The computer acts like a super literal bouncer, checking a list from top to bottom. First, is the score 80 or higher? Nope, it's 75. Okay, moving on. Next check. Is it 60 or higher? Yep, it is. So it prints good, and then its job is totally done. It won't even look at the rest. It only gets to that final else if none of the other conditions are met.
All right, so we can handle multiple paths. But what if we want to ask more detailed, more specific questions? This is where we start creating smarter logic, using the power of three little words: and, or, and not.
The and operator? It's the strict one. For the whole thing to be true, every single piece connected by and has to be true. It's the bouncer at a club. You must be over 18, and you must have a valid ID. If you're missing even one of those, sorry, you're not getting it. Now, this might look a little technical, but it's super simple. It's called a truth table, and it just shows you every possible outcome. Look at that. There's only one single row where the final result is true, the one where both condition A and condition B are true. If even one part is false, the whole thing is false. It's totally all or nothing. Now, the or operator, it's way more laid back. It only needs one of its conditions to be true for the whole statement to be true. It's like your parents saying, you can watch TV if you finish your homework or you clean your room. You don't have to do both, just one is good enough. And you can see this right here in its truth table. Look how different this is from the and table. The only way you get a false is if both sides are false. If there's even a single true in there anywhere, the whole thing becomes true. It's basically the polar opposite of that strict and operator.
And finally, we have the not operator. This one's the easiest of all. Think of it like a light switch. It just flips the value. It turns a true into a false and a false into a true. So if you can go out only if you are not sick, it just means the code is checking if is sick is false. Simple as that.
Okay, so now let's put it all together and see how these simple things can build a really powerful rule. To get into this event, you must be registered. That's an and, a hard requirement. You also have to be either early or know someone. And finally, one last check, you must not be banned. See how those little operators all stack up to create one complex, really intelligent decision? So you might be thinking, this is all a bit abstract, code and logic, but the truth is, you interact with this stuff constantly. Let's look at how these rules actually build the apps and websites we use every single day. Every single time you log into a website, the system's checking if your email and your password match what's in the database. When you buy something online, the code is checking if the payment was successful before it does anything else. And in a game, the code is in a constant loop, checking if your player's health is less than or equal to 0. Your banking app, it's using this logic to check if your balance is less than 0 to label your account as overdrawn. And every modern website you visit on your phone, it's checking if your screen width is below a certain size, and if it is, it shows you the mobile-friendly version. This is the invisible engine that powers our entire digital world. Ultimately, that's what this all boils down to. It's not just some programming feature. It's the fundamental way that we give a computer a brain. It's how we give software the ability to react, to adapt, and to make what feels like intelligent choices. And you know what? Understanding this isn't just some fun fact. It's literally your first, most crucial step towards learning how to code, because it teaches you how to think like a computer. So here's the bottom line, the most important takeaway from all of this. Once you grasp this way of thinking, the simple structure of if this, then that, with some ands and ors thrown in, you've basically unlocked the secret. If you can understand how computers think, you can tell them exactly what to do. Every single intelligent feature in the software you love, from a simple login screen to the most complex video game, is powered by these very simple decisions. You've just learned the fundamental language a computer uses to think. So, the only real question left is, what are you going to teach it to do next?